Welcome to Bethlahem Institute of Engineering. Bethlahem Institute of Engineering is affiliated to Anna University, Chennai and approved by AICTE, New Delhi. This institution was established in the year 2008.
Good morning. Let's see the design of cantilever retaining wall. Normally there are two types of retaining walls are there. One is cantilever retaining wall and the another one is counterfort retaining wall. Cantilever retaining wall and counterfort retaining wall. This topic included in the subject structural design and drawing for final years. Let's see the design. For example, in the question given that a cantilever retaining wall to retain an earth embankment with a horizontal top 4 meter above the ground level. That is, the height above the ground level is 4 meter and the density of earth is 18 kilonewton per meter cube. Angle of internal friction pi is 30 degree. Safe bearing capacity of soil is 200 kilonewton per meter square. And the coefficient of friction between soil and concrete is 0.5. Adopt M20 grade concrete and Fe4 and 5 HOSD bars. Grade of concrete is M20 and the grade of steel is 415. First, we want to write the given data given in the question. The given data given were angle of internal friction and it is denoted as pi is equal to 30 degree and the SBC means safe bearing capacity of soil is 200 kilonewton per meter square. And the coefficient of friction between soil and concrete, it is denoted as mu. I am not noted here and the coefficient is denoted as mu. Okay, mu is 0.5 and the grade of concrete is M20 and the grade of steel is 415. These are all the data given in the question. And we know that the density of earth, that is density of soil is 18 kilonewton per meter cube and also the density of concrete is 24 kilonewton per meter cube. That's not given in the question. We all know that. Okay. The solution, the first step is dimensions of retaining wall. Okay, first step, we want to find the dimensions of retaining wall. Okay, in order to find the dimensions of retaining wall, the first we want to find the minimum depth of foundation. Okay, at first we want to find the minimum depth of foundation. The formula to find the minimum depth of foundation is Q0 divided by nu into Ka square. Minimum depth of foundation is Q0 divided by nu into Ka square. Q0 is safe bearing capacity of soil. Q0 means safe bearing capacity of soil. It is given in the question. The value of safe bearing capacity is 200 kilonewton per meter square. Nu means density of soil. It is also given that density of earth is 18 kilonewton per meter cube. Okay. Next we want to find Ka. Ka means active earth pressure. Ka is active earth pressure. The formula to find active earth pressure Ka is equal to 1 minus sin pi divided by 1 plus sin pi. Pi means it is given angle of internal friction. Pi is 30 degree. Okay. So, K is equal to 1 minus sin 30 degree divided by 1 plus sin 30 degree, which is equal to 0.33. Thus, the minimum depth of foundation is equal to Q0 divided by nu into Ka square. The value of Q0 is 200, nu is 18 and Ka is 0.33. Thus, we get the value of minimum depth as 1.23 meter. Next, we want to find the overall depth capital H. The overall depth capital H is equal to 4 plus 1.23. 4 means the height above the ground level, which is given in the question. The distance above the ground level is 4 meter, that is 4 plus 1.23. 1.23 means minimum depth of foundation, which is equal to 5.23 meter. Next, we want to find the thickness of base slab. After founding the depth, we want to find the thickness of base slab. The thickness of base slab formula for cantilever retaining wall is H by 12. Okay, capital H by 12. Capital H means overall depth. 5.23 divided by 12. We get 0.43 meter. Take it as 0.45 meter. Okay, that is 450 mm. And next, the small h. Small h means the height of the stem. Okay, the height of the stem. The retaining wall included 3 parts. Okay, retaining wall included 3 parts, that is the stem part and the base slab. Base slab means in the base slab is divided into 2, toe slab and heel slab. Okay, h means the height of the stem, right? Height of the stem. Height of the stem means we already found the thickness of base slab. Thickness of base slab is 0.45 meter and the height of the stem is overall depth is 5.23. 5.23 minus the 0.45. Okay, 5.23 minus the thickness of base slab, we get the height of the stem 4.78 meter. Okay, the next step is width of base slab. Okay, width of base slab. In the cantilever retaining wall, the width will be in the distance between 0.5 h to 0.6 h. Right, 0.5 h to 0.6 h. 0.5 h means 0.5 into h. H is the overall depth. The value is 2.615 and 0.6 h means 0.6 into 5.23, that is 3.13 meter. So, the width is in between 2.6 to 3.1, right? The width is in between 2.6 to 3.1. Take it as 3 meter, right? Take it as 3 meter. The next is we want to find the toe projection, right? Toe projection. Toe means in the bottom portion the slab is there, right? In the slab, the 1 meter distance is the toe, right? The 1 meter distance part is the toe. Toe projection, the cantilever retaining wall, the formula to find toe projection is B by 3. B means the width of the slab. Already we found the width of the slab. B is 3 divided by 3, that is 1 meter, right? Next, we want to assume the width of the top of the retaining wall. Take it as 0.2 meter, assuming the distance, right? 0.2 meter. Okay, this is the first step, dimensions of retaining wall. The dimensions of retaining wall, first we are finding the minimum depth of foundation, next overall depth, next thickness of base slab, next width, next toe projection, then assuming the top width, right? Okay, the next step we are going to design the stem. Okay, we are going to design the stem. In the question, the grade of steel given is Fe 415. Okay, the grade of steel given is Fe 415. For Fe 415 grade, the factored moment formula is Mu is equal to 0.138 FCK BD square. Right? Mu is equal to 0.138 FCK BD square. Right? From this formula, we are going to find the D again. Right? Yes. From this formula, we are going to adopt a thickness of the stem D. Right? For that, the formula for Fe 415 grade is Mu is equal to 0.138 FCK BD square. Right? In this, we are going to find D. For that, we want factored moment Mu. Right? Factored moment Mu. In order to find the moment Mu, the formula is M is equal to Ka omega h cube by 6. Right? In order to find the factored moment, first we are finding the bending moment at the base of stem. Right? Maximum bending moment at the base of stem. The formula is what? M is equal to Ka omega h cube by 6. Ka is active earth pressure. In the first step itself, we find out the value of Ka, active earth pressure. And the omega is density of soil. It is given in the question that 18 kilonewton per meter cube. Next, h is height of the stem. Already we found, right? From the overall depth minus the width of base slab, right? 4.78 divided by 6, right? So we get the maximum bending moment as 108.2 kilonewton meter, right? 108.12 kilonewton meter. From this, the factored moment mu is equal to moment into factor of safety. Moment value is 108.12 into factor of safety 1.5, that is 162 kilonewton meter, right? Substitute the value of mu in the above equation for FE4 and 5 grade. Substitute the value of mu in the above equation. The equation is mu is equal to 0.138 FCK BD square. All the other data we know, right? Mu is 162. Next, FCK is the grade of concrete given as 20. Next, B for 1 meter, right? We will design the B, take it as 1 meter, right? And the D value is 242.27. We get the D value is 242.27. It is very small, right? Already we assume that the top width of the stem is 0.2 meter. Right, but here we got the D value as 0.24. It is very small, so take it as 450 mm, right? Take the value of D as 450 mm, right? Because the shear stress at the base moment, right? Shear stress moment at the base will be more, right? Shear stress is more at the base, so take it as 450 mm. Next, we are going to find the reinforcement details. First term, right? Okay, to find the reinforcement detailing, refer IS 456-2000, code IS 456-2000, page number 96. The formula is given. Mu is equal to 0.87 Fi AST D into 1 minus AST Fi divided by BD FCK. In this equation, we are going to find the value of AST, right? All the other data we know. Okay. Mu value is factored moment, right? Mu is factored moment, already we found. Next, 0.87 Fy is grade of concrete. Grade of steel. Fy is grade of steel. AST, we want to find the value of AST. Next, small d. Small d means capital D minus cover, right? Capital D minus cover. We adopt a thickness of 450 mm. 450 minus cover, that is small d is 400 mm, right? The thickness is 450 mm minus cover, that is small d. So small d is 400 mm into 1 minus AST into Fy. Fy means grade of steel 415 divided by B. B is for 1 meter, right? B is, we are designing for 1 meter. So take it as B is 1 meter or 1000 mm, and small d. Small d means 450 minus 50, that 400. Next, FCK is grade of concrete 20, right? It is given in the question. From the above equation, we get AST is equal to 1195 mm square, right? 1195 mm square. And next, we want to find the spacing in between the reinforcements, right? Next, we want to find the spacing. The formula to find spacing is area of 1 bar divided by total AST into 1000, right? The formula for spacing is area of 1 bar divided by AST into 1000, right? Next, we want to find the area of 1 bar. So, assume a 12 mm dia bar, right? Assuming the main reinforcement at 12 mm dia bar, right? So, area of 1 bar is equal to pi by 4 into 12 square, right? The dia of the bar is 12. So, area of 1 bar is equal to pi by 4 into 12 square divided by AST. Total AST we already find out 1195 into 1000. From this we get the spacing as 94.64, take it as 100 mm. So provide 12 mm diabars at 100 mm center to center spacing. Next, distribution reinforcement. For the cantilever retaining wall, the distribution reinforcement, take it as 0.12 percentage of BD. In the code they denoted as 0.12 percentage of BD, that is 0.12 divided by 100 into B is 1 meter, same as the previous step, 1000 mm into D. D is overall depth, okay, D is overall depth, that is 450. Included the cover depth, that is we get the distribution reinforcement area is 540 mm. Next we want to find the spacing for the distribution reinforcement. Spacing formula is area of 1 bar divided by AST into 1000. Assume the dia of bar as 8 mm dia, okay, assuming 8 mm dia bars for distribution reinforcement. So the spacing is equal to pi by 4 into 8 square divided by AST 540 into 1000, that is 93.08, take it as 100 mm. Okay. The next step we want to find the stability calculation, right? Stability calculation, that is the maximum and minimum pressure. We want to find the maximum and minimum pressure. For that, first we want to find the total load and total moment in the cantilever retaining wall, right? The first in the third step is stability calculation. In this step, first we want to find the total load and total moment, okay. For that, we are dividing the section into 3 parts, right? We are dividing it into 3 parts, that is W1, W2 and W3, right? W1, W2 and W3. W1 means load due to the stem, right? W1 means load due to the stem, that is above the base slab. W2 is the load acting in the base slab, right? Load due to base slab. And W3 is load due to backfill, right? Backfill means the soil part, right? The soil part, okay. First we want to find out W1, that is the load due to the stem, right? First we are going to find out W1. W1 means the load due to stem. See, in the diagram itself we understood that the stem part is in trapezoidal manner, right? The stem part is in trapezoidal manner. So we are dividing the stem part into 2, that is one rectangular portion and one triangular portion, right? We are dividing the stem part into 2, one rectangular portion and one triangular portion. First, we are going to find out the load in the rectangular portion. Okay, we are going to find out the load in the rectangular portion. The formula to find out the magnitude of load is area into density, right? Area into density. For the rectangular portion, the area is B into D into density, right? Stem is concrete. So B into D into density of concrete. See, look at the diagram. The B is 0.2, right? In the rectangular portion, the W1 part, right? W1 part, the rectangular portion B is 0.2 and D is the height of the stem, right? D is the height of the stem, that is 4.78 into what? Density of concrete, that is 24, right? Density of concrete is 24. And the triangular part, look at the stem, the triangular part, the magnitude of load is area into density, same. The area of the triangle is half BH, right? The area of the triangle is half BH into density, that is half into B. B, what is the B here? The total B of the stem is 0.45. In the rectangular part, the base is 0.2. Upper remaining 0.25, right? Half into 0.25 into H is 4.78 into density of concrete 24, right? We get the magnitude of load as for the triangular part it is 22.8 and the rectangular part it is 14.25, right? Next we want to find the distance from A, right? For the stem part, next we are going to find out the distance from A. From A, that is the centroidal distance, okay? The centroidal distance, that is AB distance plus the rectangular part distance, the base of the rectangular part by 2, right? The AB distance is 1.55, okay? The AB distance is 1.55. AB means the heel slab, right? AB means the heel slab. The heel slab distance is 1.55 plus 0.2 by 2, okay? Centroid, same as centroidal distance. That is 1.65, and the triangular part 1.55, that is the distance from A, that is AB, plus rectangular part width, that is 0.2, plus triangular part width is 0.25 by 3, okay, because it is a triangular part, so it is 0.25 by 3. The answer we get is 1.85, okay, 1.85. Next we are going to find the moment of all the forces, right? Moment of all the forces. Moment is equal to load into distance, right? Load into distance. Okay, load we got that 22.5 into distance is 1.65. So for W1 we get 37.62 for rectangular part, and for triangular part we get 26.06. Next, the second step is W2, right? For W2 we are going to find out the magnitude of load for base of the slab, base slab, right? Base slab. It is easy, right? Because the base slab is in rectangular manner, right? Rectangular manner, and the B is 3, and the D is, the depth of the slab is 0.45, and the density of concrete is 24. So we get 32.4. Next, the distance from A is, it is in only one part, so 3 by 2, 1.5. Next moment is load into distance, 32.4 into 1.5, we got 48.6. Next, W3 is soil, right? Soil part, the backfill, the earth part, the soil part. So take it as in rectangular manner. B into D into density. B is the width of the heel slab, right? Because the backfill is above the heel slab. So the same width will come for backfill and heel. That is 1.55 into the height. The height is same as stem height. So 4.78 into density of soil is 18. We get the value as 132.5. And the distance from A, only one part is there, the backfill, so 1.55 by 2, we get 0.775. Next, moment of all forces, that is load into distance, 132.5 into 0.775, we get 102.67. okay. Next, we are going to find out the moment due to earth pressure. Moment due to earth pressure, that is, the formula is Ka nu hq by 6, right? Ka nu hq by 6. Ka means active earth pressure, nu means density of soil, h is the height of the stem, right? 4.78 q by 6, the value we got is 108 kilonewton meter, right? Next, we want to add all the loads, right? All the loads we got, that is W1 plus W2 plus W3, right? In W1 there are two loads, that is, one load is for rectangular part and the another load is for triangular part, 22.8 plus 14.25, plus the load for W2 is 32.4. Next load in W3 is 132.5. That is, the total load is 201.95. Next, the total moment is, we got for W1, the moment is 37.62 plus 26.06. Next, for W2, the moment we got is 48.6. Next, for W3, the moment we got is 102.69. Next, the moment due to earth pressure is 108. Therefore, the total moment is 322.9 kilonewton meter. Okay. The next step is we want to find the maximum and minimum pressure intensities. Okay. We want to find out the maximum and minimum pressure intensities. For that, we are going to find out the distance of point of application of resultant force Z. Right, distance of point of application of resultant force Z. The formula for Z is total moment by total load, right? Total moment by total load. Total moment is 322.9 divided by total load is 201.95. That is the distance of point of resultant force from A Z is 1.59 meter. Okay. Then we are going to find out the eccentricity value. Eccentricity E is equal to Z minus B by 2. Okay. The eccentricity should be less than B by 6. Right. The intensity should be less than B by 6. So Z value is 1.59 minus B. B means the width, right? Width of the slab 3 by 2. We got the eccentricity as 0.09. It is less than B by 6 because the B by 6 value is 0.5. So we got the eccentricity as 0.09 meter, right? Next, maximum and minimum pressure intensity. The pressure intensity formula is summation W divided by B into 1 plus or minus 6C by B, right? For maximum pressure, it is 1 plus 6C by B, and for minimum pressure intensity, it is 1 minus 6C by B. Okay, so sigma max is equal to total load divided by B into 1 plus 6C by B. All the data we know, right? Total load 201.95 divided by B is 3 into 1 plus 6 into E. E is eccentricity 0.09 divided by 3. Therefore, the maximum pressure intensity is 79.43 and the minimum pressure intensity is 55.2 kilonewton per meter square. Okay. Next, we are drawing the pressure intensity diagram. In the pressure intensity diagram, the maximum pressure will come below the toe slab, that is 79.43, and the minimum pressure will come below the heel slab, 55.2 kilonewton per meter square. Next, by interpolation method, we are finding the pressure intensity below the stem, that is x and x1, right? By interpolating the pressure of heel and toe, we found the value, we found the pressure in pressure below the stem, right? That is the maximum pressure is 79.43 for 3 meter distance, right? Next, for at the stem, the pressure is 55.2. Thus, we are interpolating it. 3 by 24.2 is equal to 2 by x. From this, x is 16.13. Same 2 by 16.13 is equal to 1.55 by x1. Thus, we are getting all the values. The pressure is 55.2. Next, it is increasing to 67.7. Again, randomly it is increasing to 71.33. Then going to 79.4. Okay. The next step is design of heel slab. In the heel slab, 2 downward forces and 1 upward soil pressure will be there, right? In the heel slab, 2 downward forces, that is downward weight of backfill above the heel slab. Next, downward weight of the slab. Next, upward soil pressure, that is below the slab, right? Below the soil pressure. Totally 3 loads, right? 3 loads. Okay. The same tabular column. First is the weight of backfill, that is the downward weight, right? Downward weight, B into D into density. The width of the backfill is 1.55 above the heel slab. Next, height of the backfill means height of the stem, that is 4.78 into 18, that is density of soil. Backfill is soil, so density of soil. We got the value was 133.36. Next, distance from B, that is 1.55 by 2, width by 2, we got 0.775. Next, moment is load into distance, 133.36 into 0.775, that is 103.35 kilonewton meter. Next, the weight of heel slab, that is area into density. The area of the slab is 1.55 into 0.45 into 24, that is grade of density of concrete. We got the value was 16.74. Next, distance from B, width by B, okay, 1.55 by 2, we got 0.775. Next, moment is equal to load into distance, 16.74 into 0.775, we got 12.97. Add the 2 downward loads, right? Add the 2 downward loads, 103.35 plus 12.97, that is 116.32 kilonewton meter, right? Next, we are going to find the upward pressure, that is we already drawn the pressure intensity diagram, right? Pressure intensity diagram. In this diagram, the AB, look at the diagram, the AB, right? AB, the pressure below the AB, right? The pressure below the AB. It is divided into 2 parts, one rectangular part, one triangular part, right? One rectangular part and one triangular part. In the rectangular part, how we will get the pressure? How we will get the moment or load? How we will get the moment? First, we want to find the load, right? First, we want to find the load for the pressure, for the upward pressure, right? In order to find the load for pressure, the formula is B into pressure. Okay, B into pressure. See, look at the diagram for rectangular part. The pressure is 55.19, right? The pressure below the heel slab is 55.19, right? That is B value is 1.55. 1.55 into 55.19. We got the load as 85.54, right? Next, the distance same for rectangular part by 2, right? Distance by 2. 1.55 by 2, that is 0.775. Next, moment is equal to load into distance. 85.54 into distance, 0.775, that is 66.29, right? It is for the rectangular part, the pressure for rectangular part. Next, we are going to find out the upward pressure for the triangular part, right? Triangular part. Triangular area is half B into pressure, right? Half B into pressure. Look at the diagram. Look at the diagram for the triangular part. Below the heel slab, half B is 1.55 into pressure is 12.5, right? 12.5. So, we got the value as 9.6, and distance is for triangular part width by 3, right? Width by 3, 1.55 by 3. We got the value as 0.52, right? Next, moment is equal to load into distance. 9.6 into 0.52. We got the value as 5. Add the two upward pressure, right? Add the two upward pressure. We got 71.29. The next step, we are calculating the net bending moment. Okay, we are calculating the net bending moment. How the difference between the two pressure, right? Upward load minus downward moment, right? Upward moment minus the difference between the two moments, the downward moment and the upward moment. Okay, here the downward moment is more than the upward moment, right? So, downward moment minus upward moment. The net bending moment is equal to downward moment minus upward moment. Downward moment is 116.32 minus 71.29. That is, the net bending moment is 45.03. Next, we are calculating the factored moment. Moment into factor of safety. Factor of safety value is 1.5. 1.5 into 45.03, we got 67.5 kilonewton meter. Next, we want to find the reinforcement detailing for the heel slab, right? Reinforcement detailing for the heel slab. We know the formula to find AST. The AST formula is mu is equal to 0.87 Fy AST D into 1 minus AST Fy divided by BD FCK. We got the value of AST as 479 mm square. Next, to find the spacing, assume 12 mm dia bars. The spacing formula is area of 1 bar divided by AST into 1000. The area of 1 bar pi by 4 into 12 square divided by AST is 479. We got the value as 236. Take it as 200 mm. Okay. Provide 12 mm dia bars at 200 mm center to center spacing. Next, we are finding the distribution reinforcement. Same as the previous step, 0.12% of BD, same value we will get here also, 540 mm square. Assume 8 mm dia bars for the distribution reinforcement. The spacing we got is 93.08. Take it as 100 mm. Okay, provide 8 mm dia bars at 100 mm center to center spacing. Okay, next step, we are designing the toe slab. Okay, designing the toe slab. In the toe slab included, same as heel slab, two downward loads, right? Two downward loads. That is the weight of the toe slab, then the distance below the ground level, right? Distance below the ground level. That is, the overall depth is, we know, the overall depth is 5.23, right? The overall depth is 5.23. Height above the ground level is 4 meter, right? Height above the ground level is 4 meter. Height below the ground level is 1.23 meter. Totally 5.23. Above the ground level is 4. Then below the ground level is 1.23. In the 1.23, 0.45 meter is for slab, right? 0.45 meter is for toe slab. The remaining height is soil above the ground level. That is okay. And the remaining height is soil above the ground level. The height will be around 0.78 meter, right? Above the soil above the ground level. The soil above the ground level. The height of the soil above the ground level will be 0.78 meter. Okay. Then the weight of the toe slab. These two loads are in downward loads. Then the upward loads, look at the pressure intensity diagram. DC part is the toe slab part, right? DC part is the toe slab part. Here also included two areas. One is one rectangular part and the other one is one triangular part, right? Okay, first we are going to find out the weight of the toe slab. Weight of the toe slab, the formula is area into density, B into D into density. B, the width of the toe slab is 1 meter and the depth is 0.45 into density of concrete is 24. We got the value as 10.8. Then the distance, it is in rectangular manner. So B by 2, 1 by 2. We got 0.5. So moment is equal to load into distance. 10.8 into 0.5, we got 5.4. Next, the weight of the soil, that is above the toe slab. B is same the width of toe slab, 1 meter into D. That is below the ground level 0.78, right? 0.78 into 18 is the density of soil. We got the value as 14.04. Next, distance from C, that is 1 by 2. We got 0.5. So the moment is equal to load into distance, 14.04 into 0.5. We got the value as 7.02. Next, upward pressure, same as the previous step. Okay, B into pressure. Next one is half B into pressure. Okay. Here the upward pressure is more, right? In this the upward pressure is more, so the toe section moving upward. Okay, so the toe section will tend to move in the upward manner. So adopt the reinforcement at bottom, right? Adopt the reinforcement at bottom. Next we are finding the net bending moment, that is upward pressure minus downward pressure, because the upward pressure is more in this step. 38.4 minus 12.42, we got the value as 25.98 kilonewton meter. Next we are finding the factored moment into factor of safety. We got the value as 38.97 kilonewton meter. Okay, next finding the main reinforcement, same as the previous step. Moment formula, mu is equal to 0.85 AST D into 1 minus AST Fy divided by BD FCK. The AST value we got is 274 mm square. In order to find the spacing, adopt 12 mm dia bars. The spacing value we got is 287 mm. Take it as 250 mm. So provide 12 mm dia bars at 250 mm center to center spacing. Next, the distribution reinforcement 0.12% of BD. So provide 8 mm dia bars at 100 mm center to center spacing. Okay. In the step 6, we are going to find out the safety against sliding, right? Check for safety against sliding. That is, we are going to find out the factor of safety, right? Factor of safety. We want to get the factor of safety value will be 0.5 or more. If the value will be less than 1.5 or more, okay, we surely we want to get the value of factor of safety as 1.5 or more. If we will get the value less than 1.5 means we want to provide shear key, right? We want to provide shear key. Okay, or else we will stop in this step. Okay, check for safety against sliding. For this, we want to find the factor of safety. The factor of safety formula is mu W divided by P, right? Factor of safety is equal to mu W divided by P. Mu W means maximum frictional force, right? Maximum frictional force, mu into W. Mu is coefficient of friction. It is given in the question, 0.5 into load, total load, right? In the stability calculation step, we found the total load, right? W1 plus W2 plus W3. Summation W, 201.95. The value is 100.97. Next, P means total horizontal earth pressure, right? P means total horizontal earth pressure. The formula is Ka omega h square by 2, right? Ka omega h square by 2. Ka is active earth pressure 0.33 into omega is density of soil 18 into h is overall depth 5.23 square by 2. The value of P is 81.2 kilonewton. From this, the factor of safety is equal to mu W by P. We got the value as 1.2. It is less than 1.5. Right? Hence, the structure is unsafe against sliding. Hence, we have to design shear key. Right? Hence, we have to design shear key. The width of the shear key will be equal to the width of heel slab. Okay? the depth of the shear key will be equal to the depth of shear key. So in the step 7 we are designing a shear key. The depth of the shear key is equal to 450 mm. Right? The depth of the shear key will be 450 mm. We want to find the force in shear key. Right? We want to find out the force in the shear key. In order to find the force in the shear key, we want to find the intensity of stress. Right? Intensity of stress in front of shear key. The intensity of stress in front of shear key formula is Kp into sigma max. Right? The intensity of stress formula is Kp into sigma max. Kp value is 1 by Ka. So, Kp formula, Kp means passive earth pressure. Passive earth pressure is inversely proportional to active earth pressure. That is Kp is equal to 1 by Ka. Kp is equal to 1 by 0.33. Next, the intensity of stress is equal to 1 by 0.33 into maximum pressure. Already we found out the maximum pressure is 79.4. We got the intensity of stress as 240.6 kilonewton per meter square. So, the force in the shear key is equal to that intensity of stress 240.6 into area 0.45 into 1. We got the force in shear key PP is 108.33 kilonewton. Okay. Next we are finding the factor of safety again, mu W plus the force in the shear key divided by P. We got the value as 2.58. Hence it is safe. Next, we are going to find out the reinforcement detailing in shear key. As per the code, minimum percentage of steel reinforcement is 0.3 percentage of BD. Okay. For shear key, the minimum percentage of steel reinforcement is 0.3 percentage of BD. That is 0.3 divided by 100 into B is 1000 into 450. AST is 1350 mm square. Then provide 12 mm dia bars. The spacing we got is 83.75. Take it as 100 mm. Okay. In the 8th step, we are going to find out the check for shear stress. Right? Check for shear stress. In order to find the check for shear stress, we have to find out the nominal shear stress and permissible shear stress. Right? We want to find out the nominal shear stress and permissible shear stress. The nominal shear stress value should be less than the permissible shear stress value. Right? The nominal shear stress should be less than the permissible shear stress value. Nominal shear stress formula is tau V is equal to Vu by Bd. Right? Nominal shear stress tau V is equal to Vu by Bd. For that we want to find out Vu, that is factored shear force. For that we are going to find out the net shear force value. Net shear force formula is V is equal to 1.5 P minus mu W. 1.5 into P is horizontal pressure, P is total horizontal earth pressure. Okay, P is total horizontal earth pressure minus mu W, that is maximum frictional force. The value we got is 20.83. Next, factored shear force means net shear force into factor of safety. 1.5 into 20.83, we got 31.25. From this, the nominal shear stress value will be 0.07 Newton per mm square. Next, we are going to find out the value of permissible shear stress. The permissible shear stress value is taken from the code IS 456-2000, page number 73, table 19. For this, we want to find out the value of 100 AST by BD. We got the value of 100 AST by BD as 0.3. By interpolating, we got tau C as 0.834 Newton per mm square, which is greater than the nominal shear stress tau C, hence safe. Next, we want to draw the reinforcement detailing, the main reinforcement and distribution reinforcement for stem, heel, toe and shear key. Okay. Hope you all understood this. Thank you.